Select the best reagents to accomplish the following transformation. So we're going to take a look at our starting material and the product. And so we can see that the starting material is an acid chloride. And the product is an aldehyde. So our acid chlorides are the most reactive of our carbonyl compounds. And so if we were to take an acid chloride and reduce it, because this is a reduction, we're adding hydrogen. If we were to use either of our two typical reducing agents, so lithium aluminum hydride or sodium borohydride, both of these will reduce your acid chloride to give you the alcohol. So it actually give you a primary alcohol. Right? So in the case of this acid chloride, your product would be the benzyl alcohol. So you would have added two equivalents of hydride to what used to be the carbonyl. So if we're stopping at the aldehyde, this is stopping at the intermediate stage. So you need a selective reducing agent. And so you need something that's not as reactive as lithium aluminum hydride or sodium borohydride. And so these reducing agents are often recognizable as modified forms of either lithium aluminum hydride or sodium borohydride. And so if we look at B, this is actually the right answer, but let me draw out the structure of this. So you've got your lithium, and so this is related to LAH, lithium aluminum hydride. You can see it's only got one hydride and it's got three of these tert-butoxy groups. So here's your aluminum, it's got one hydride and three of these tert-butoxy groups. So what we're doing with this structure is it's less reactive than lithium aluminum hydride. Right? We don't have as many hydrogens that can be transferred. And you also, this has a negative charge on that aluminum, you also have these electronegative oxygens that can help to share that negative charge. So it's not as reactive. So you've got only one hydrogen that can be transferred, or hydride, because it's really being transferred as H-. And then these tert-butoxy groups also tone down the reactivity because the oxygen is electronegative. So that helps to share the burden of that negative charge, so it's a less reactive hydride. And then you also got a lot of steric hindrance. So this is how we're able to control this reaction and have it just add one equivalent of hydride. And another key factor is the temperature. This does have to be done at low temperature to help slow this reaction down. So when you see the combination of what looks like a modified version of either LAH or sodium borohydride at this low temperature, there's a good chance you're doing a selective reduction. So we'll see that this is the reagent that we use to take an acid chloride if we want an aldehyde. We will see a different reagent that works much the same way to take an ester and make an aldehyde.